Okay, for this next video, we're going to take a look at the 68, 95, 99.7 rule. We'll also start to get into z-scores. But before we get started, I want to make sure that you have two different PDF files I think will be really useful in completing these exercises. And if you don't, a quick Google search for at least the one is going to bring you to some information. So the first thing I'm going to show you is what's called the z-score chart. And if you do a simple Google search of the AP Stat Student Resource Packet, and I just want to give credentials here where they're due. This is from the College Board. It's for the AP exam, and I think it's pages 4 and 5 is where you'll find the Z-score chart. So I'm on it right now, 4 and then 5. It looks a little maybe intimidating, a little crazy. It looks very mathematical, and statistical, but we'll break it down. It's really not too bad. So that's the first thing you need. The second thing I created for those of you in my class, this is a PDF I just put together as kind of like a guide to helping you complete these problems. So what I would recommend doing, and this is only for if you're having trouble visually with these problems, is to print off a couple copies of these and to use this for each different problem. And it saves you a little bit of time. It takes you step by step what things to use and the rules to use. And I found that a lot of students do like it. So hang on to these two PDF files, and we'll get to those in a little bit. But let's take a look at this set of data here first. And we have two quantitative variables here. We have age and salary. And we're going to use age because we're going to assume that that distribution is symmetric. As we've mentioned before, the distribution of salary is not symmetric. Rather, it's skewed right because typically you'll have certain players on teams that earn a lot of money. Courtney Lee is one of them. Noah is another guy who's earning 17 mil a year. Porzingis, he'll be up there soon enough. As he gets older, he'll earn more money, and those salaries bring up the average, and it's a lot more of an outlier towards the upper end than it is towards the lower end. So it should be skewed right. Let's just double check and see what that shape actually looks like. Should be a way to create. Oh, it's not coming up. Let's try this. Salary. Let's highlight this column. Sometimes that makes it work. Histogram of salary. Here we go. And if I take a look at this chart, not hugely skewed right. It's a little bit of a weird looking distribution, but I can see most of my salaries are going to occur. Let me make this a little bit bigger. Between 0 and $3.6 million, right? 7 of them are between that. 4 of my players are between 3.6 and 7.2. And then I have one player over here who's making between 10.8 and 14.4, and then 3 players between 14.4 and 18 million. So it is a little bit skewed right. It's definitely not normal. It's definitely not symmetric. So I can't use 68, 95, 99.7. I can't use z-scores either. I'd have to use my 5-number summary to describe this distribution. So let's scrap this for now. Let's go over to age and look at that histogram. Once again, Google Sheets can be a little weird. So, okay, here we go. This works. Now, compare it to this distribution, right? The salary distribution. Distribution of age, I still wouldn't say it's perfectly symmetric. It might be a little skewed to the right, but it's definitely more normal. And for this case, we're going to assume normality. All right, we're going to assume that this distribution is normal. So we have 4 people between the ages of 19 and 23, 7 people between the ages of 23 and 27, so on and so forth. So just kind of take a mental picture of this histogram and know that our z-scores and our 68, 95, 99.7 rule is going to be useful in helping us predict percentages for this distribution. So I'm going to delete that for now, okay? And I'm going to get out of this menu right here, and I want to just sort these columns by column B to get them in order according to age. So we're going to sort the range according to column B, A to Z, and there we go. Okay, so now we're listed our players from youngest to oldest. All right, now the next thing I want to do is calculate two different values, the mean and the standard deviation. All right, and the mean for this age I could do is equal to the average of this whole column. So the average age of the Knicks is 25.8 years old. And then my standard deviation, there's also a function for this. Standard, I think it's actually STDEV. Here we go. And we're going to highlight this column. And it's 4.3. Okay, I'm going to round, just for the sake of this exercise, since it's the first time that we're looking at these values, I'm going to round these to the nearest number. Okay, so there is a way to do this. Insert format. I think it's under data. Well, you know what? To save a little bit, let's just write it off to the side here. So we're going to round this to the average age of 26, and we're going to round this to the average age of 24. Okay. Now, this standard deviation is pretty big relative to this distribution of ages, because we only have 17 people on the team. But let's say we wanted to apply these two numbers just based on the Knicks. We wanted to use these two numbers to describe the distribution of ages in the NBA. All right, this 4 probably wouldn't be practical. It's a little bit too high, but let's use it nonetheless. Okay, so remember these two values. Average age is 26, standard deviation is 24. And I'm going to jump back to my notebook, and I'm actually going to use that PDF of that step-by-step process on calculating percentages. Okay, so let's make this a little bit bigger. And once again, my goal with this is to answer some questions on the likelihood of players being between certain ages and them not. So let's calculate the mean and the standard deviation, which we did first. And I'm just going to write off here to the side. The mean, it was 26, and the standard deviation was 4. And then fill in the blanks in the density curve, okay, is my next step. So in the middle is 26, and then one standard deviation away is 30. Notice I'm just going to add 4 each time that I do this. 38, and then do the same thing in this direction. We'll do 22. We'll go 18, and we'll go 14. Hopefully now you're starting to see why that standard deviation of 4 is not that practical, okay? Because based on our 90, 68, 95, 99.7 rule, what we're saying is that 99.7% of the NBA population is between the ages of 14 and 38, okay? No 14-year-olds playing in the league, and 18-year-olds don't really play in the league anymore either. So, most of your players are going to be between the ages of 22 and 34. Once again, it's not a perfect normal distribution, but we're going to use it for the time being. So let's say I asked you the question, what percentage of players are younger than 30? Okay, how could I answer that question? And what I'm going to show you here today is that you can use this 68, 95, 99.7 rule if you want, okay? Up until this point, it's the only option that we've looked at, but there's a thing called z-scores, and z-scores work for any value, okay? And I'll explain what that means in a second, but to answer this question, let's try and use this rule first. So what percentage of players are younger than 30? And let's think about tracing that section and be this section over here all the way back down around again. And I know from 22 to 30, all right, if I want to kind of break this thing down, I know that 22 up to 30, I know that's 68%, right? All of this in here is 68%. So it's at least 68%. Furthermore, I know that this region here, basically from 18 to 34, is 95%. So from 18 to 22 would be 13.5%. Okay, now I could keep going section by section and figuring out, okay, what's between 14 and 18 and what's below 14. Some of you are probably thinking to yourself, well, why are we making this more difficult than it has to be? Okay, couldn't I just say, if this is the middle, this is symmetric right here where 26 is, isn't less than 26 50%? So in other words, isn't this whole region over here, isn't all this 50% in white, or I'm sorry, in yellow? Okay, and your answer would be yeah, it definitely is. This is all this section here. Okay, that right there is 50%, right? So let's try and figure out what the region over here is. And if I can just add those two together, I'll have my answer. Okay, well, I already know between 22 and 30 is 68%. So half of that, this region right here, from 26 to 30 is 34%. So 34 plus 50% together answers my question, what percentage of players are younger than 30? And that equals 84%. And that's my answer. Okay. That's answering that question using the 68, 95, 99.7 rule. Let's say I wanted to use z-scores. All right, z-scores is something totally different. And to explain this, I'm going to start from scratch and actually erase everything in here. And show you how this works. All right, so now for z-scores, let's start with where z-scores are practical. Let's say I change this question, what percentage of players are younger than 31? All right, and I'm just going to put 31 above that 30 for now. 31 is like right over here. Notice how it's not specifically one standard deviation above. It's not two standard deviations above. It's kind of in between. It's kind of in between, right? And it doesn't really give me a fair estimate of like what that number would be, right? So what I've got to do here is use something called a z-score for a number that's not actually one standard deviation above or one standard deviation below. I'm, for this sake, still going to use 30, okay? So if I follow these step by step, these steps, I'm going to shade in the area of interest. So less than 30 or younger than 30 is going to be basically everything to the left, all the way over here, right? All the way over. Okay. And I know it's already 84%, but how do I use a z-score? Okay. Well, z-score has this following formula down here, and this is very important to know. What I'm going to highlight right down here. The observation minus the mean divided by the standard deviation gets me my z-score. Okay. So what does that look like in written form? Z is equal to my observation, and I'm just going to capitalize OBS minus the mean all over the standard deviation. And students often ask me, well, what is the observation? And I always say, don't worry about it. Wait till last to figure out what that number is, right? The mean in this case I know is 26. The standard deviation in this case is 4. Well, the only other number that's in question here, the only number I'm using is this 30, right? What percentage of players are younger than 30? It's the number that's in question. That's your observation. So kind of taking that idea over to my equation here, 30 is my observed value. So z is equal to 30 minus 26 over 4, which is equal to 4 divided by 4. And I'm going to write this number. You're probably thinking, why am I going to write this with 2 decimal places? 1.00. And you'll see why in a second. Okay. 1.00 is not my percentage, it's my z-score. Okay. Now, what does that z-score do for us? It tells us a couple things. It tells us that this observation 30, okay, and let me highlight this. This observation 30, because it has a z-score of 1, right down here, it tells me that 30 is 1 standard deviation above the mean. Okay. If that number was 1.2, I'd say 30 is 1.2 standard deviations above the mean. Okay, that's the theoretical definition of a z-score. Okay, practically what it is for us, it's the middleman. Okay, so if you go to a store, and you're going to buy toothpaste. Okay, there's a middleman that buys that tube of toothpaste in bulk. Right, they're going to buy it from a distributor who's got 100,000 packs of it, and then they're the middleman. They're the ones taking it from the factory to the store. Okay, this z-score is a middleman. It's going to take your observation to a percentage, right? How do we get from 30 to 84%? We have to use our middleman, the z-score. Okay, so we're going to look up that value of 1 in the corresponding probability in the z-score chart. Okay, so take that 1, and I'm going to jump around a little bit, so hang with me. And open up that AP resource packet. We're going to go back down to our z-score chart. And what I'm trying to find is the z-score of 1.0. Okay, and this is how a z-score table works. The first page, they're all negatives. Okay, and I'm looking at that very first column, right? The first column they're all negatives. The second column are positives. Okay, so I'm looking for a z-score of 1.0. Okay, 1.0 is right here, specifically this highlighted section right here. Notice how in that cell I have 1.0, and then my 100th column I have another 0. If my z-score was 1.13, I go down I go down a row, and then I go over to 0.03. So a z-score of 1.13 would be 80.8708. But for now, I'm just interested in this guy right here. 1.00 is 0.8413, and that always represents the probability to the left of your z-score. Okay, so the likelihood that I get a z less than 1, or in this case an observation less than 30, or a player younger than 30, is 84.13%. Okay, so 84.13%. And how we write that is the probability that z is less than 1.00 is equal to 8.8413. And more specifically, how do I answer this question? What percentage of players are younger than 30? I would say it's 84.13%. Okay, these are so close in value, these two numbers, the 84% and the 84.3, that you can use either one. You can use z-scores, or you can use our 68, 95, 99.7 rule. Okay,